To master engineering chemistry, we must discard the idea that it is a random collection of reactions to be memorized. It is a strictly governed, interconnected logic system. The laws dictating quantum probability scale directly into thermodynamics, which then dictate macro-level materials. Our objective here is precise, decoding dense chemical theory into an actionable framework. We are mapping the exact mathematical traps and conceptual pitfalls that cost students marks on university exams. The highest density of these errors occurs at the atomic level. Classical intuition, the idea of electrons orbiting a nucleus like planets around a sun, fails completely here. To accurately predict atomic behavior, we must abandon planetary models and rely entirely on probability mathematics. If you want to engineer the macroscopic materials of tomorrow, you must first mathematically conquer the microscopic traps of the atom. In 1924, Louis de Broglie proposed that classical physics could not explain electron behavior. He introduced wave-particle duality, stating that every moving particle has an associated wave. The mathematics for this is lambda equals Planck's constant over mass times velocity. The exam mnemonic here is heavy mass, tiny wave. Because wavelength is inversely proportional to mass, a macroscopic object like a cricket ball has a wavelength so astronomically small it is unobservable. But for a subatomic particle like an electron, the wave properties dictate its entire existence. Werner Heisenberg proved that observing these microscopic waves has strict limitations. It is impossible to determine simultaneously and with perfect accuracy both the position and momentum of a subatomic particle. This brings us to a massive exam trap. When calculating the uncertainty principle, the formula requires Planck's constant divided by 4 pi. Do not use h over 2 pi. That single error invalidates the entire calculation. To define the state of these uncertain particles, we use Erwin Schrödinger's wave function, denoted by the Greek letter psi. But psi itself is purely mathematical. It carries zero direct physical meaning. It is only when we square the wave function, psi squared, that we extract physical reality. This represents the probability density. It shows us a three-dimensional heat map of exactly where an electron is most likely to be found. Accepting electrons as these diffuse probability clouds, rather than tiny planets on fixed tracks, provides the correct mathematical framework. This is the only way to accurately predict how specific elements will bond and react. Inside a multi-electron atom, outer valence electrons do not feel the full positive charge of the nucleus. The inner electrons physically block or shield that attractive pull, creating what we call effective nuclear charge, or Z effective. We calculate this shielding constant, sigma, using Slater's rules. The system requires grouping the electron configuration and applying a strict set of multipliers. Memorize this sequence. Same 35, previous 85, old 100. Let's calculate the shielding for the outermost 3s electron in sodium. Any other electrons in the same principal group contribute 0.35. Since our target electron is the only one in the 3s group, this contribution is 0. Next, we look one shell inward, to the n-1 shell. The 8 electrons in the 2s and 2p orbitals each contribute 0.85 to the shielding effect. Finally, all electrons in the n-2 shell, or deeper, contribute a full 1.00. That gives us 2 electrons from the 1s orbital. Our total shielding constant is 8.8. Subtracting that from sodium's atomic number of 11 yields an effective nuclear charge of 2.2. This shielding dictates orbital energy levels. It explains why the 4s orbital fills before the 3d orbital during the Aufbau building process. But remember the key exception. Transition metals will always lose their 4s electrons before their 3d electrons when forming ions. Mastering Z effective allows you to map the logic behind atomic size, ionization energy, and the entire periodic table's reactivity. Moving from individual atoms to macroscopic systems brings us to thermodynamics. Every chemical reaction is a physical tug-of-war between two forces: enthalpy, the drive to minimize total energy, and entropy, the drive to maximize disorder and randomness. Gibbs free energy resolves this conflict. This equation combines enthalpy and entropy at a specific temperature to determine if a reaction is spontaneous. If delta G is negative, the process can perform useful non-expansion work. When calculating Gibbs free energy, students consistently fail on unit conversions. Enthalpy is almost always provided in kilojoules, while entropy is given in joules. You must convert these to a matching unit before you subtract, or your final answer will be completely wrong. This thermodynamic energy directly translates to electricity. The Nernst equation maps abstract free energy onto the measurable voltage of an electrochemical cell, factoring in the number of electrons transferred and the concentration of the reactants. As a battery discharges and approaches equilibrium, the cell potential drops. When equilibrium is reached, E cell hits zero. We use this exact mathematical condition to solve for the equilibrium constant, K. Thermodynamics provides the strict mathematical framework required to engineer working circuits, predict chemical feasibility, and power modern devices. To harness that thermodynamic voltage, we construct an electrochemical cell. This requires an anode where oxidation occurs, a cathode where reduction takes place, and an electrolyte to allow ion flow while preventing short circuits. The traditional lead-acid battery demonstrates this through standard galvanic corrosion. The spontaneous redox reaction generates heavy, reliable current, but it physically degrades the internal lead plates over time. Modern electronics rely on the lithium-ion battery. For the exam, you need the specific architecture. It uses a graphite anode, intercalated with lithium, and a lithium cobalt oxide cathode. This operates on a rocking chair mechanism. Instead of degrading the metal, lithium ions cleanly shuttle back and forth between the two electrodes during charge and discharge. Because metallic lithium reacts violently with water, this system strictly requires a non-aqueous organic electrolyte. By manipulating ionic movement across a calculated chemical potential, we generate the portable, high-density energy necessary to untether society from the electrical grid. Scaling up some ions, we reach macroscopic material strength through polymers, massive macromolecules formed by linking thousands of repeating monomer units. The thermal behavior of these materials is best remembered with a simple exam mnemonic: butter versus bread. Thermoplastics, like low-density polyethylene, consist of individual linear chains. They melt when heated and can be reshaped repeatedly, like butter. Thermosetting polymers rely on three-dimensional cross-linked networks. Once they are cured by heat, they harden permanently, like baking bread. In 1907, Leo Baekeland applied this cross-linking principle to create Bakelite, the world's first fully synthetic plastic. The exam trap here lies in the synthesis stages. Condensing phenol and formaldehyde first yields a linear thermoplastic intermediate called Novolac. It only becomes Bakelite in the second stage, when a catalyst forces extensive cross-linking, permanently locking it into a rigid thermosetting grid. That rigid, infusible structure makes Bakelite an exceptional electrical insulator and highly heat-resistant, properties that cemented its use in early automotive and electrical engineering. Decades later, Wallace Carothers developed a completely different polymer structure through step-growth condensation polymerization to synthesize nylon 6,6. The 6,6 indicates that both of its monomers, hexamethylene diamine and adipic acid, contain exactly 6 carbon atoms. Their condensation eliminates water and forms highly regular amide linkages, bound tightly by hydrogen bonds to create a fiber with immense tensile strength. Controlling the geometry and bonding of a molecular backbone dictates whether the final macroscopic material acts as a flexible parachute canopy or an impenetrable electrical shield. Conventionally, plastics are strict insulators. However, conducting polymers break this rule. By engineering an alternating single and double bond system, a conjugated pi electron backbone, and introducing chemical dopants to create charge carriers, these polymers can actually conduct electricity. The discovery of doped polyacetylene earned the 2000 Nobel Prize in Chemistry, effectively bridging the gap between flexible organic polymers and rigid semiconductor electronics. We have mapped the logic. Prepare your screens and capture this matrix. This is the condensed architectural framework for your exam. Always write out the full electronic configuration in proper groupings before applying Slater's multipliers. In thermodynamics, verify your joules to kilojoules conversion before calculating Gibbs free energy, and know exactly which catalysts synthesize which polymer structures. Engineering chemistry operates on strict, predictable mathematical laws. Master the calculations, recognize the unit traps, and you will secure